Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Epen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@epen.info. My guest today is Professor Daniel Wang, who is Professor of Astronomy at the University of Massachusetts, Amherst. His research interests span examining various high-energy sources of the interstellar medium, characterizing the global structure as well as the physical and chemical states of hot gas in and around galaxies, investigating the interplay of high-energy radiation and gas with other galactic components, and exploring the interaction of galaxies with their environment. Welcome, Dan.
Thank you very much. Thank you for the introduction.
Yeah, thanks for doing this. So I want to start with one of your earlier papers from 2013, Dissecting X-ray-Emitting Gas Around the Center of Our Galaxy, in which you say most supermassive black holes are accreting at very low levels and are difficult to distinguish from the galaxy centers where they reside. Our own galaxy's SMBH, supermassive black hole, provides an instructive exception, and we present a close-up view of the quiescent X-ray emission based on 3 megaseconds of Chandra observations. So before we get into the details of this, Dan, do you go by Dan or Daniel?
Either way will be fine.
Okay. So before we get the details of this, I want to set the context of supermassive black hole. So we have the Milky Way. We assume, or are we close to proving that we have a supermassive black hole at the center of our galaxy?
Yes, actually, the last year's Nobel Prize in physics was awarded to the discovery of the supermassive black hole at center of our galaxy. So two teams were responsible for the observations of the evidence for the supermassive black holes based on the orbits of stars very close to the center of our galaxy, because these stars move so fast that indicates the large concentration of mass in a very small volume at the center of our galaxy. That gives you really convincing evidence for such concentration of mass. The only logical explanation is the supermassive black hole. And then a few years ago, I think maybe 2 or 3 years ago, another Nobel Prize in physics was awarded to discovery of the shadow of a supermassive black hole, but not for our supermassive black hole, but for a relatively nearby galaxy, which for good reason, which was observed first. So we do see the shadow. That's a really telltale evidence for the real the prediction of supermassive black hole. So for our galaxy, we know the big central concentration of mass that is naturally be explained by supermassive black hole. For a nearby galaxy, M87, we know actually see the shadow of supermassive black holes. That's a clear confirmation of, I mean, the concentration for mass is due to actually the black hole.
It's an amazing thing, Daniel. So Einstein should be turning in his grave here. So we took a photograph of a supermassive black hole in M87, and Andrea Getz and the German team, they're sort of looking at the motions of stars around our own galactic center. Seems to imply that there is something really massive there in very small amount of space, right? So,
Yeah.
so do we have an estimate of what the mass of that might be?
No, actually, I should clear one statement. Actually, the discovery of the shadow of the supermassive black hole at the center of M87 still not awarded Nobel Prize yet. Was that actually, I was a little bit confused a few minutes ago. The Nobel Prize was awarded to discovery of the gravitational wave for a merger of the kind of more low mass supermassive, low mass black holes. Because
Yeah.
that's all about the black holes. So that okay. So sometimes you get confused. Yes. So the discovery of shadow of the black hole is yet to be awarded a Nobel Prize. Now back to your question is if I recall, actually, could you repeat your question a little bit?
Yeah, so I was just wondering whether we have an approximate estimate of the mass of the supermassive black hole we have
in,
in
in,
Milky Way.
in Milky Way, that's about 4 million suns mass.
4 million solar masses.
Yeah.
So in the grand scheme of things, it's sort of a small black hole, a small supermassive black hole, would you say, or?
Yes, in the mass spectrum of black holes, the black hole at the center of our galaxy is relatively small. But still more than a million solar masses. I mean, it's not at a. So we know actually now these days down to about, let's say, a really small fraction of that, something like 10 to 5 or 0.1 million suns mass kind of black holes also have been discovered in nearby galaxies.
Yeah, so is the M87 one where we actually sort of got a shadow, a
Yeah.
picture? Is that really big, SMPH?
Yes, that is much bigger black hole than our black hole at center of our galaxy. So when a black hole is big, but of course, the M87 is more distant. So in terms of angular size in the sky, actually the black hole at center of M87 is comparable to the black hole at center of our galaxy. The reason the discovery of shadow was first made for the M87 is because physically the black hole at M87 is bigger, and the bigger that means the change is slower because things need to information need to be conveyed from one part of black hole around the black hole to another part will takes time. So the time scale will be much longer. But so our black hole is smaller, so light crossing time is much shorter. Therefore, it tend to change or vary rapidly. So makes it much more difficult to make a picture if things are moving around.
Yeah.
Okay, because things do move around because black hole by itself not emitting things, but they're all accreting matter around from the surrounding, which producing some light. So the shadow is against the light emitted by the material around the black holes. So the black hole itself, you don't see it, right? So you see the shadow. So when things changes rapidly, so you have to make a movie instead of a picture. That's to make the imaging of the shadow of our galaxy black hole much more difficult than the black hole at the center of M87.
Mm. That's interesting. So going back to the paper, um, our own galaxy, there's a lot of dust. We are actually in the galaxy, so quite difficult to see to the center, right? So looking at X-ray, that gives us some advantages.
Absolutely. Just like we're not able to see your stomach, so you have to go to hospital, right, to take an X-ray. So X-ray can go through your body and see the shadow uh, of your bones, your stomach, whatever. Because densities will be different ways of your body or different parts of your body will will basically absorb the X-ray differently. So that's basically the way we're kind of seeing towards the center of our galaxy, going through the large amount of gas and dust uh, on the way to the center of our galaxy.
So most of the dust and gas in our own galaxy, do I understand this correctly, Daniel? It doesn't really emit X-ray. So X-ray emitting gas is close to the center.
Actually, everything in the universe emits to the X-ray to some degree. Okay, so this is of course stars. They are called interstellar gas. Okay, they all emit kind of X-ray or reflect X-rays to some degree. But compared to the center of our galaxy, which of course is confusing, but you still can see a discrete emission from individual objects if they are relatively bright against the background. So our black hole is not active. It actually is very faint. That makes it essential to use high resolution camera or telescopes and to observe any emission from around the black hole of around center of our galaxy.
So I don't know much about this, Daniel. So as the gas and the gas, generally speaking, falls into the black hole, it's a pretty violent process, right? So in that process, it's going to emit a lot of X-rays.
Yes, actually, so you can one way to think about it is black hole has a big concentration for mass in a very small volume. Therefore, gravitational potential is very deep, just like water falling through the waterfalls, right? You just coming down, speeds up, I mean, accelerates, get to the bottom, you get a splash, right? So now the gas kind of falling into the a cliff, like kind of like around the black holes, just accelerates towards the black hole. And of course, gas then will collide with each other. Also, there's side motions of the gas that will not be able to get into the black hole immediately. It's like you pour the water into your kitchen sink. The water will not get into the sink immediately. They go around to dissipate the energy, okay, of the motion. So that, of course, here we're talking about a big, deep potential. There's a lot of energy will be released before or the motion needs to be dissipated before the matter or in this case gas can get into around black holes. So that process will basically leads to the heating of the gas to tens of hundreds of million degrees. That kind of we call it plasma now is because the electrons will be separate from their nucleus, then so it become charged particles, and this plasma or ionized gas will basically emit the X-ray.
Yeah. And so in this 2013 paper, you say these results provide important constraints for models of the prevalent ra- uh, radiatively inefficient accretion state. And so our early measurements, so this was before the Chandra satellite. This paper was written in
No,
2013,
no,
was
this
before.
actually was way after Chandra was launched about more than 20 years ago. Okay,
Okay.
so this is a way which we use 3 million uh, seconds of Chandra's exposure to get this good enough data, so we can educate the spectral, not only the imaging but
Yeah.
also the spectroscopic information, basically how the photons coming out of this very hot plasma distribute according to different energies of the photons. That gives you kind of fingerprint about the properties of the plasma in terms of temperature, in terms of chemical abundance, things like that.
Yeah, this might be a bit technical. What do you mean by radiatively inefficient accretion state?
Oh, okay, that's a very good question. Actually, we know essentially all major galaxies, like our own, will have these days supermassive black holes as their centers. So almost every galaxy, yeah. But the majority of them will not be active. So there are small fraction of them are very active, and they called active galactic nuclei. So which basically, or sometimes called quasars. You can see them at the edge of the universe, so because they are very, very bright, although they
Yeah.
are very, very distant. So that's only a small fraction of such supermassive black holes because they are accreting a lot of dense materials around, especially in the early universe. Okay, so there's a lot of materials in individual galaxies. So these are called quasars or active galactic nuclei, are very, very bright. In contrast, the supermassive black hole at center of our galaxy is very faint because there's hardly much material, there's not much dense materials for the supermassive black hole to accrete from. The reason is actually there's uh, big clusters of massive stars around the supermassive black holes. They were formed like a few million years ago. Okay, so that time, during that formation period, there was a lot of cold gas around. So there might be a big uh, episode of emission, just like active galactic nuclei. That was millions of years ago. But the formation of the massive stars around the black holes will lead to some consequences because massive stars also emit called winds because they are very, very energetic. So
Yes.
they are producing winds which move at speed something like a few thousand kilometers or miles per second. That's a really strong winds. So the strong winds tend to expel any residual cold materials away. Okay, so there's not much cold materials in the immediate environment of supermassive black holes. Kind of prevent the black hole to accrete uh, large amount of matter, therefore large amount of energy to be produced.
Yeah.
So the black hole only thing to do is to accrete this very hot wings. So wind is very energetic, density is low, but very hot. So it's hot meal is difficult to eat. Yeah.
Yeah.
So basically it's only small because hot is even with very strong gravity, it's very difficult to grab these hard materials. Okay, their density is very low and very hard to capture. That basically is an ingredient to make the black holes uh, very, very dim because they hardly have anything getting into the black hole or falling into the potential. Okay, so but this probably represents such faint supermass black holes represent kind of silent majority of black holes in the universe at the present universe at least.
Yeah.
Yeah.
Yeah, that's really interesting. So, as you say, the quasars, when they formed many, many billions of years ago, they had a lot of materials to essentially eat, so to speak.
Yeah.
In the current state, if you look at the Milky Way, SMPH, most of the material has been either blown away or already concentrated into stars around SMPH. So it doesn't really have a lot to eat, looks like, right?
Yeah, things a little more complicated, I would say. I mean, yes, compared to early universe, the amount of gas is relatively small, or density is low.
Mm.
But the gas still falling towards the galaxy. Actually, the whole galaxy I will call the ecosystem. Okay, it's evolving ecosystem. So this still gas falling towards the galaxy from the intergalactic space. Okay, so yes, you have star formation, which a lot of mass has been locked into the individual stars. But the gas is still being accumulated to some degree. So this always continuous formation stars. Then the stars will produce energies. Like I mentioned, this fast winds from massive stars, but also the massive stars will die very soon. They will produce called supernova explosions at the end of their lives.
Yeah.
So they produce a lot of energy, which tend to expel the gas. So the whole galaxy is this kind of ecosystem. Yes, you have gas falling in, then you form stars. Stars have this kind of feedback, energetic um, outbursts, which you can tend to expel things. So
Yeah.
kind of, on long term, there's much kind of balance. So stars be continually formed, but at a much slower pace compared to things at the early universe. So
So,
yes, so
yeah.
around black holes, you still forming stars every maybe few million years. Then the stars will die. Okay, the massive
Yeah.
stars die, the gas start to get accumulated towards center again. Then you will have another episode of star formation and maybe active galactic nuclei phase.
Yeah. So will it be correct in assuming then um, the SMPHs in galactic centers, they would be active infrequently. When they become active, it's going to be active for a period of time, and they go dormant again, and they'll be active again. Is that the way to think about it?
Yes, that's excellent. That's basically like I would say something like a whole universe like Christmas trees. And the kind of flash, as centers of these galaxies, and the come and the goes. But yes, but the brink, the active phase of the supermassive black holes tend to be short-lived. Okay, so they just come and goes, but most of times become more kind of silent, for quite a long time. That's why at the present universe these days the black holes normally account for active ones on account for like a few percent of all the population of the supermassive black holes.
Yeah, yeah. I want to go into one of your recent papers, AzTEC Survey of the Central Molecular Zone, increasing spectral index of dust with density. So what is the AzTEC Survey?
So AzTEC is a camera which installed on the large millimeter telescope of our university, the University of Massachusetts Amherst, and the Mexico counterpart, and joint developed the
Yeah,
telescope. And so this is just so AzTEC is one camera which like a heat sensor which is sensitive to kind of millimeter wave radiation. It's like a micro oven kind of
yeah,
wave. Okay,
yeah,
that is another ways to look at the universe. Okay, so this is a better way to observe cold gas, dense cold gas, which can accumulate at some distance from supermassive black holes. But there's some concentration we call central molecular zone, okay, that contains a large fraction of the dense gas in our galaxy, waiting to form stars.
So why do you call it a molecular zone? Because it's cold?
Because this gas is very dense and very cold, so they tend to form more molecules. So most of the gas in the molecular phase, so we call it a molecular zone.
Okay, and so from the supermassive black hole, what is the distance we are talking about for the zone?
So
How
we
far is
call
it? Yeah.
this region is actually about something like 1,000 light years across, or a little more than that, depending how. So roughly speaking, about 1,000 light years across.
Okay, and so the supermassive black hole itself, all the activity that goes on around it, we are talking about a few light years, right? So this
And
is
yeah, it's
much,
much smaller. Yes, so this we're talking about less than 1 light years.
less
So
than one
much
light.
much
Okay.
of the emission
Yeah.
actually we observe from the around supermassive black hole comes in the region much smaller. So that's amazing things. The size of the influential size of black hole even much smaller. Okay, and so the event horizon is much smaller, like more like size like a solar system, okay, kind of size. Then now, what analogy I will make is now compare the size of black hole with the whole galaxy. So if the black hole is size of say a quarter U.S. quarter coin.
Yeah.
So what size of galaxy we're thinking about? Would you guess?
The United States, maybe?
Yeah, close. The whole, basically whole globe, whole Earth. That's a galaxy. Okay. Then since a black hole with size of coin will have very large influence of how that whole galaxy evolves and how it works. Actually, have a lot of connections. Now that is the size of black holes, the coin. Then the influential regions around it for cold gas will be like my room here. Okay, that's the size. The coin will have direct gravitational influence, can grab things around this room size. Okay, beyond that, it's very hard to grab because things don't move around to again, so you cannot grab easily. Okay, so yeah, so now the material around the base a much larger size than my room here, so around the room around in my backyard here. Okay, that's a so large concentration of matter. So that's kind of configuration we're talking about, which but still kind of interact with each other.
So, so what do you learn from this cold molecular zone? What did we learn in the context of the black hole itself? Do we get some ideas from there?
Yes, of course, the materials around it, around my room here, it certainly will have some kind of immediate impact potentially because since I'm moving around, around. So at some point, and some things will falling towards the black holes, and the stars will be forming from these dense cold materials. Okay, that's actually we know it's a big concentration of matter there. Then sooner or later will forming stars. And
Yeah.
stars then formed will expel, because these energetic outflows will push the materials around. So some materials will get into the very center. Maybe eventually get accreted by the black holes or forming stars around black holes. So things in the universe now in our galaxy, especially near the center of our galaxy, is very dynamic. So they are moving fast, tend to be denser, and tend to have big concentration of gas or stars. So that means I will call basically center of our galaxy to be downtown of a big city, right?
Yeah.
So I'm in Amherst. I will consider to be like a suburb, way away from suburb. But much of the action, sometimes even violence, happens at the downtown, right? So of course, it's something good, something bad there. But so that's the things. I mean, what happens in the downtown, of course, we know affects us, right?
Yeah.
Because actions, have city government or whatever, what the big decisions or big actions will affect the rest of the country even sometimes, right? So the whole galaxy works like that. So but that basically downtown of a galaxy plays a disproportionately important role because there's a lot more actions there. So they tend to expel things out. Not only they just forming things there, falling towards the center, but they also have lots of spill out in terms of energy, in terms of mass, in terms of uh, 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 elements which synthesize in the stars there. So basically, how that the whole galaxy evolves with time.
Hmm.
So exchange.
Yeah, so this molecular zone, it's a little bit like a garbage collection process.
Oh well, yeah. No, I mean, of course, life goes cycles. Like,
Yeah.
I mean, universe does recycles very well. So they and now yes, so the materials get contaminated. So originally, we can pristine materials maybe falling from intergalactic space contains very small amount of say metals. By metals, I mean heavy elements like oxygens, irons, which build our body or even the Earth.
Yeah.
So initially, there's no such elements. So these all elements we are talking about here, we see around here were all originally synthesized in the cores of stars. And these stars, when they die, they will spill out some of them,
Yeah.
okay, back into intergalactic space, and then the material cools down, become denser, and eventually forming new generation of stars. The generations after generations, and we start to have more and more such elements. Eventually, our sun formed from there. Then around the sun, then form the Earth. Earth is made of these heavy elements. Okay, eventually, life developed, right? So which we now are living basically. We basically they call it a star dust, right? It's all the waste from stars.
So, so what we learn from this cold molecular zone, you say here there is a deficiency of large grains or a fundamental change in dust optical properties. So, so what did we learn from the CMC about either the black hole or the Milky Way in general?
Now, again, I want to emphasize. So we are living in an ecosystem. So every component of ecosystem matters. Okay. So you want to say if we have a climate change, of course, right? Because ozone, and because you emitted too much carbon, put too much carbons into the atmosphere, things like that.
Yeah.
So here in the AzTEC, the image we are talking about is we are seeing the dust. Okay, dust actually matters a lot. Dust is the kind of ingredient you need to uh, to cool the materials and to shield the radiation, otherwise it will penetrate into clouds, which to then allow dust with the gas to collapse to form stars. So dust actually is a very important ingredients in the evolution of all the life cycles of gas and the stars.
Yeah.
Okay, so without that kind of dust, the things were difficult to evolve. Okay, and so difficult. So just like in a certain aspect of the atmosphere, we need to have. Then if you change it, and you change a lot. So here now we are trying to measure the property of the dust. Okay, so that we need to if we want to understand how this ecosystem works, right? And how fast stars can form, okay, and when stars will form, we need to understand dust, their properties. So basically, whether what kind of what's the population of dusts? Dust, how big they are, how they tend to absorb or emit material as light, and it matters. So so these days astronomy is very called astrophysics. Is to understand how things work. So first thing to do is to understand their properties. So what we did is to measure the property of dust in this case, therefore how they might affect the evolution of the clouds and why the clouds will be sitting there, for example, not actively forming stars. So we want to know when the stars will be forming and what will be the life cycles of such a material.
Yeah, yeah. And I want to go into your latest paper, Daniel. So Chandra large-scale mapping of the galactic center, probing high-energy structures around the central molecular zone. Before we get into the paper, could you talk a bit about Chandra? What exactly is it, and sort of the history of it?
Okay, so everybody knows Hubble, right? Hubble have produced so many spectacular images, but these images are mostly in the visual light that our eyes are sensitive to. Okay, so visual light only is small part of the electromagnetic wave we're talking about. So visual light is only a small part of that. Okay, so to understand the universe, we need to understand not only the visual light. Actually, a glass center, for example, will not be seen in the visual light because of the dust obscuration. So that's why we need to go to X-ray. X-ray will be in a much energetic part or shorter wavelength of the this electromagnetic wave. Okay, so Chandra is one of the NASA's four great observatories. Okay, so I would call Chandra as the uh, X-ray astronomy, the Hubble of X-ray astronomy, which is capable to make sharp images, X-ray images of the universe. Okay, compared to the Hubble, which can make sharp images of visible universe.
Yeah. Is it still operational?
Yes, Chandra is still operational, just like Hubble. Okay, so other two telescopes will be Spitzer telescope, which operated in the infrared. Okay, and the other one called gamma ray telescope, and the which also is no longer working anymore. Died years ago. Yeah.
And so when was Chandra launched? How long has it been up there?
If I recall it correctly, is 1999.
Oh, wow. Okay, so it's still
Yeah.
going after 20 years.
Oh yeah, and I'm still healthy and still operating. It's still very difficult to get time, observing time on telescope. Demand for time is still huge. You know, means it's so many questions still yet to be answered.
And so it is just measuring X-rays, and so the large scale mapping. So 20 years of data, I would imagine we have a lot of data now. Was it sort of specializing in our galaxy, or was it looking just like Hubble all over the place?
No, these observations, almost all of them were made specifically for the center of our galaxy or something extension from the center of our galaxy. So this whole region we have mapped covers something like 40 moon size. So if you know the size of moon in the sky, which is about half degrees across. So you basically put the moons together, about 40 of them, the whole image. So this is quite big areas.
Yeah.
So Chandra will take image on a small, very small part of it, okay, for each image. So over the time, 20 years, we accumulate lots of images. So the newest map was produced by combine all these observations plus some of my new observations, okay, to fill all the gaps, remaining gaps between the previous coverage, and producing, stitch them together, produce a continuous coverage of the entire region, which is like a 2 degrees times 4 degree regions. So not only the central molecular zone part, which only covers like a central band in the middle, but also away in north and south, away from central molecular zones, to study basically how the central molecular zones interacts with the rest of the galaxy, the connection to the rest of the galaxy.
And so we found a lot of interesting features in the center of the galaxy, right? Could you talk a bit about what we found?
Yes, we found basically this love vertical structures. That means away from central molecular zones. Okay, okay. So that means there's a good connection between the activity in central molecular zones with even larger properties, actually larger structures we know previously from other observations, like Fermi bubbles, that are kind of gamma ray bubbles on scale, on scales which comparable to the size of our galaxy. So this is much smaller. But the connection between the two had been unclear. So now with these images, we start to see the specific features, okay, in X-ray. So hot gas seems to be flowing out from the central molecular zones into these larger scale structures. And also, more importantly, actually, there are narrow features, very narrow features, which were hardly observed, which only previously were observed in the central molecular zones. And we find, because now with these new observations, we start to see these narrow features. Not only they are there, but they also to be positionally coincide with features seen in the radio. Okay, which radio kind of filaments. Okay, these are filaments which have been a mystery for a long, long time, which was actually discovered a long time, but don't know how these radio features. They're all energetic features, but the coincidence between the X-ray and the radio, which is totally on the opposite side of the electromagnetic wave. Okay, one seems to be on a very longer wavelength, one at a very shorter wavelength, seem to be very different, but they are actually in the same position. But actually, longer wavelength does not mean the process which produces it is low energy. Okay, it actually was. It's known actually to be produced by very high speed charged particles called cosmic rays. Cosmic rays basically are moving at speed very close to the speed of light. So
Yes.
these are energetic particles, just more energetic than the people can produce in the super colliders. Okay, this is much more energetic. And this kind of charged particles moving in a magnetic field or producing radio emission. So radio emission is not very energetic, but the process that produce such a radio emission is very energetic. Now we start to see the X-ray emission from the same region. That coincidence is very difficult to understand. Cannot be explained by any well-known mechanisms. like pulsars. Pulsars is a kind of magnetized, fast rotating neutron stars, kind of remnants of the massive stars, which tend to be speed very fast. I mean, so spins very fast, therefore producing cosmic rays. Or by supernova explosions, which tend to producing very high-speed ejectors, which can accelerate particles and heat gas. But such narrow features actually cannot be explained by such well-known phenomena. So only thing left is kind of called a magnetic field reconnection. That is actually a pretty well-known phenomena for our sun, because sun is very close. Actually, we know there's a lot of things happens near surface of the sun. Okay, called like solar flares, or solar winds. Okay, solar winds is basically produced by flares or big flares, ejection, which affects the community even when they arrive at the Earth. They will even interrupt the communications, because all these are because charged particles, very energetic ones. So actually, so we know actually magnetic field reconnection is responsible for producing solar flares. But such a phenomenon was predicted for the interstellar space, which is totally different kind of environment from the around the stars, because it's magnetic field much stronger. But it was predicted, but never been seen. Yeah. So now, as I believe this coincidence of X-ray threat linear features with the radio filaments provides most convincing evidence for the reconnection, because the reconnection we know can produce both hot gas and accelerated particles. So which will produce naturally the X-ray emission from hot gas and the radio emissions from the cosmic rays moving around the magnetic field.
So what do you mean by magnetic reconnection? What exactly is that?
Okay, magnetic field is a little bit hard to understand. So magnetic field is basically something like a rubber band. Okay, it's some tension. Okay, so magnetic field is kind of energy you think about. So of course, the magnetic field is important to generate electricity, things like that. But the magnetic field basically is not only like a rubber bands. You can is not it has tension. Okay, rubber band tension, but it's energy. Okay, but also magnetic field has directions. We know magnetic field have north, have south. Okay, so that means it has direction. So one interesting aspect about the magnetic field is when two magnetic fields of opposing directions get together, kind of force together, they tend to annihilate.
Yeah.
Something like matter-antimatter annihilation.
Yeah.
Okay, but of course a little bit more complicated here. So basically, it's so energy stored in the magnetic field, but in opposite kind of direction. If in magnetic field they meet together, because fundamentally magnetic field is produced by currents, electricity. Okay, current. So basically, different direction of magnetic fields means different direction of currents. Yeah. So when two currents meet opposite direction would meet together, they tend to cancel each other because they all dissipate, collide with each other, producing energy. That's basically is the source of energy. Kind of release or reconnection means, or sometimes called annihilation. Okay, because of course it's not a complete annihilation. So some magnetic field reconnect with each other, then producing tensions, which actually producing also is kind of energy source. But whatever, whether it's reconnection or annihilation, produces energy.
So these filaments that we observe, are they predictably sort of orthogonal to that connection? Do we know precisely how those filaments will form?
Yeah, so that's actually a little bit hard part. So that's why we tend to see all these filaments to be vertical. Yeah. So the potential mechanism to producing the opposing direction is, okay, for example, you have some pre-existing magnetic field there, okay? So say the points upward.
Yeah.
Then you now have explosion down there in the molecular zones because of massive stars, for example, have a supernova explosion, or expelled materials because of the energy input. You're producing bubble, right? You're gonna heat the gas, so bring the magnetic field outward. Magnetic field originally is kind of in the plane of galaxy in the molecular zone. Now pushed by the expansion of the hot gas. Now, in some directions, this direction magnetic field attached to this expanding bubble will have opposing direction. I mean, relative to the existing ones. So when this pushing, okay, against the background magnetic field, so it will naturally produce some regions where you produce annihilations or reconnections. That produce so that's so you see the big concentration around these outflowing bubbles or plumes, I call it. And so that's so simultaneous explains why you see the big plumes and narrow features around.
So all of what we have seen at the Galactic Center, they're all sort of within our expectations, right? There is nothing there that we can't explain currently.
To some degree, this all makes sense,
Yeah.
But it's good to first time is a kind of you see such strong evidence for such a process to occur. So once you realize, because it's always some theoretical uncertainties in predictions, theoretical predictions, okay, whether such a phenomenon could occur in such an extreme environment. Because normally you think interstellar space is pretty empty, right? It's almost it's more vacuum than vacuum you can produce in the laboratory, okay? But the volume of the interstellar space so huge. But and also again, a good point is to make is center of our galaxy is big concentration of matter or materials. So compared to the our solar neighborhood, things much more violent, much denser. Okay, so actually it's natural to observe such a phenomena, interstellar phenomena, first time towards center of our galaxy. Okay, so that's so if we understand the process, how frequently it occurs, have more such detections, so we'll reach a better understanding how frequent, how energetic, how much energy will produce, and how such magnetic field can actually bring energy from one part of the gas to another. For example, here from central molecular zones towards the halos of our galaxy. So that's kind of energy transportation is very important because so far we just have speculation. Okay, they have energy producing in one place or kind of transport to another part, but we don't know how much energy actually will be dissipated in locally here or on the way. Okay, how efficient the transportation might be. And what kind of energy, how energy will be released again. Okay, say here you have transportation through the magnetic field. Yeah. Then how the magnetic field will release energy, in what kind of fashion, whether it's mostly in hot gas or whether in the cosmic rays. So that it all affects how the one region affects another, or how the ecosystem of our gas works, because you have to know the all specifics, not just hand waving, arguments. So we basically science, right? We have some theory, have some expectations, but we also want to have observations, confirmations. Then we can move from there. Then okay, how actually things work.
Yeah, so I want to finish up, Daniel. I don't understand too much about this, but we found a long filament of approximately 3.5 billion years long, which seems like 3 times the theoretical limit. That seems to throw a wrench into a standard model. So what is your what's your feeling about this recent finding?
So what's your phenomenon?
So this I don't know exactly what they call it. So there is a structure
Uh-huh.
in the universe that appear to extend around 3.5 billion light years.
Okay, this
Uh,
is okay. I mean, beyond the galaxies, right? So this is
right,
called the large scale structures of
right,
universe.
right.
Yes, yeah. They are. I haven't followed this story closely, but big walls of materials of galaxies have been seen before. I'm not sure how this newly discovered one compared to the existing ones. Yes, in principle, we still yet to understand basically how such large scale structures form. But my understanding is the overall cosmological structures or backbones, the uh, the framework of the universe is relatively well understood. But I'll be honestly, I haven't followed this story closely to see what's new in this discovery.
Yeah, I mean, it seems like the issue is that it will challenge sort of the isotropic, sort of uniform assumption of
Yeah.
the standard model if we find them. But I guess cosmology always makes things interesting. You always find something new.
Yes, absolutely. If you find something which cannot be explained by the current standard models, actually we do have a standard model for the cosmology, then that'll be interesting. Certainly, or I mean, if the challenge, I mean, it's always steps. You have to make, to see how things can or cannot be explained, and then move on.
Excellent. Yeah, this has been great, Daniel. Thanks so much for spending time with me.
Thank you very much, and hopefully my explanation is not too difficult to understand.
Yeah, yeah. I mean, there's so much to understand.
Yeah,
So in bits and pieces,
yeah.
this is useful for general public.
Okay,
Thanks again.
my pleasure. Thank you. Bye bye.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.